My name is Samir Faruqi, and I'm a freelance trainer and consultant for Hadoop. I'm also the creator of the 2-day Hadoop Fundamentals class for Maracana. And in this demo, I'm going to walk you through the HDFS layer of Hadoop, which is a subset of the 2-day class. The first thing you should know about Hadoop is that its origins come from Hadoop, from Google white papers. There's 3 white papers, Google File System, Google MapReduce, and Google Bigtable, which become Apache HDFS, Apache MapReduce, and Apache HBase. About 95% of the architecture described in these white papers is faithfully implemented in the Apache projects. So the best place to start learning about Google File System and HDFS is really this white paper. There's some differences where in GFS, a file gets broken down into chunks, which get distributed across the distributed file system. In HDFS, a file gets broken up into blocks, which get distributed. So there's some terminology difference there. But the architecture is very, very similar between GFS and HDFS. Google released the white papers with the architecture of how these projects works, but no code was released. So it was up to a lot of the engineers at Yahoo and now many other companies who created these Java-based Apache projects. So the first thing you should know about Hadoop is understand how a file breaks up into the blocks and what that gives you. So let's say you want to read 1 terabyte of data. On the left, we have the traditional way of doing things, where we have one machine with, let's say, 4 hard drives, because it's a modern machine. And each one of these hard drives has a 100 megabyte per second capability of feeding files off disk. So we take the first terabyte of the file, and we scatter it evenly across these 4 hard drives. So we have 250 gigabytes of data on each hard drive. All right. So if you wanted to read 1 terabyte from this machine, it would take 45 minutes to read that. This is just a theoretical calculation of how long it would take to read from a 250 gigabyte drive at 100 megabytes per second. So the power of Hadoop is you take that same terabyte and you would scatter it, for example, across a 10-node cluster with 10 worker machines. And you put 1/10 of a terabyte on each one of the machines. Furthermore, let's say that each machine also has 4 hard drives. So you're putting about 25 gigabytes of data on each one of the hard drives. So across the 10 machines, there are 40 hard drives. And each hard drive is now holding about 25 gigabytes of data. And to read 1 terabyte in parallel from the 10 machines, it would only take 4.5 minutes. So by harnessing the power of multiple machines together, you can achieve your reads or writes significantly faster. Since Hadoop comes from Google white papers, it subscribes to a master-slave architecture. The competing paradigm here in the world of NoSQL is the Amazon Dynamo architecture, which is more of a peer-to-peer architecture, and that's kind of how Cassandra works. But Hadoop is a master-slave architecture, and that's the first thing you should really know about Hadoop, that the different processes or services running in Hadoop are going to be classified as either a master or a slave component. So the master components of Hadoop are the name node and the job tracker, and the slave components of Hadoop are the data node and the task tracker. We're going to be focused on the file system in this tutorial, so we're going to be more looking at the name node and the data node. The name node is the master of the file system. The data node is the slave component of the file system. There is only one name node running in a Hadoop cluster using Gen 1 Hadoop or Hadoop 1.0. And there are going to be multiple data nodes running in the cluster. So every slave machine will run a data node daemon. It will also run a task tracker daemon for MapReduce, but We're more focused with the data node daemon here. So if you have a 10-node cluster with 10 worker machines, you would have 10 data node daemons, and the 11th machine would be the name node, which is the master for the file system. You should know that the name node is a single point of availability failure. So if the name node goes down, the data nodes won't know how to make sense of the blocks that are on there. So you want to make sure that the name node is running on a dual or triple redundant hardware machine. You want to use something like RAID 1 plus 0 there. On the data nodes, there is redundancy in the fact that every file that gets stored gets 3 replicas of it, and if some of the nodes crash, there should be other nodes that have a copy of the file. Also in Gen 2 Hadoop, there is an active-passive architecture for the name node, so you can run an active name node, and if that goes down, then within a few seconds, a passive name node will come up to take over those responsibilities. However, in Gen 1 Hadoop, there is really only one name node. If that goes down, well, your cluster will not be able to read or write any files to or from the cluster. There is a secondary name node daemon as well in Hadoop, which is probably the worst named daemon in computer science, because the name secondary name node implies that if the name node goes down, the secondary name node will come up, but that's not what the secondary name node does. It does more like housekeeping for the name node. The name node, which keeps all of the file system metadata in RAM, has no capability to actually persist that metadata onto disk, right? So if the name node crashes, you lose everything in RAM, and therefore you have no file system backup. So what the secondary name node does is it contacts the name node like every hour, pulls that metadata out of the name node, and kind of reshuffles and merges it into a clean file called a checkpoint that gets written on the secondary name node. It also gets sent to the name node for persistence. So that's how the metadata in RAM on the name node actually gets persisted to a file through the help of the secondary name node. But don't think of the secondary name node like high availability for the name node. So here's the basic architecture of how HDFS works. We have a name node here with the file system metadata that I mentioned. The name node is currently keeping track of 2 files, data1.txt and data2.txt. You can see that data1.txt is actually broken up into 3 different blocks, blocks 1, 2, and 3. And data2.txt is broken up into 2 blocks, blocks 4 and 5. Now, the files themselves are not stored in the name node. This is just the file system metadata that kind of points the files towards the blocks that it gets broken up into. The other metadata in the name node is things like the file system permissions, like which users have access to a file. Also, last access time for a file is kept track of in the name node. And also disk space quotas and file system quotas are kept track of in the name node. All right, so in this diagram, we also have 4 data nodes, which are the slave components to Hadoop. And we are setting the replication factor for this cluster to 3. That's set in a file called hdfs-site.xml. And there's a parameter called DFS replication that is set to 3 in this cluster. So let's take a look at how the files actually get stored in the data nodes. All right, so file1.txt, which is data1.txt, is broken up into 3 blocks, and here's kind of how those blocks are stored in the data nodes. You can see that for each one of those blocks, like block 1, for example, there's 3 replicas made of it. So the first replica is on the second data node, and there's another replica on the third data node, and there's yet another replica on the 4th data node. Same thing with the second block. You can see that there's a replica of it here, and a replica of it on another data node, and a replica of it on the first data node. So this leads to HDFS being a highly available file system, and it's also self-healing. It's highly available because if the second data node here crashes with a copy of block 1 and block 3, that's fine because you have 2 other copies of those blocks in the cluster. And this is also a self-healing file system because if one of these data nodes goes down, then the heartbeat from that data node to the name node will cease to heartbeat. And after 10 minutes, the name node will consider that data node to be dead. And then whatever blocks were on that data node will get respawned so that the replica count 3 is achieved. The other blocks will get respawned from the other 2 remaining data nodes that should have a replica of that. All right, so that's the first file. And here's the second file, data2.txt. You can see how, once again, with the second file, we're taking the 2 blocks, block 4 and 5, and replicating it 3 times and then scattering it across the data nodes. Now, there is some intelligence to this, to how the file system actually stores the blocks across the different data nodes. So we'll talk about that in one of the future slides. The name node also has an embedded web server that hosts a kind of basic website showing statistics about the file system. So we can see when the name node was started. We can see the configured capacity of the name node. We can see how many data nodes make up this HDFS cluster. And we can see statistics about what percentage of the distributed file system we're actually using. This is just a 1-node cluster running in Amazon. So the configured capacity is only in the gigabytes range. But the largest clusters with HDFS in the world can serve up to 20, 30 petabytes of data across something like 4,500 machines for Generation 1 Hadoop. The first, I guess, confusion that some people have with HDFS is that it's a very atypical file system. So you don't actually format the hard drives in the cluster with HDFS, right? You actually format the underlying hard drives in the slave machines with ext3 or ext4. You can also use XFS. So say you have a 10-node cluster, 10 worker machines, and 1 master machine running the name node. In that case, on every one of the slave machines, you would put maybe 5 or 10 hard drives of size 1 terabyte to 2 terabytes each. And you'd have to format those slave hard drives with ext3 or ext4, because to some extent, HDFS is an abstract file system. So like the blocks come into HDFS, and then they get committed ultimately to ext3 or ext4 or XFS. ext3 and ext4 are the most common underlying file systems I see. I would recommend going with ext4 if you're starting a new cluster. And there are some configuration parameters for ext3 and ext4 that I also recommend setting, like no A time and turning on the reserved blocks. XFS can also be used for the underlying file system for HDFS, but it's far less commonly seen in my opinion. These are the common HDFS shell commands. So if you're familiar with Linux, then this should look pretty familiar. So you can run the ls command to list the directories in HDFS. You can make a new directory, copy from your local file system into HDFS. You can delete a file in HDFS. You can tail the end of a file. You can change permissions in a file. And this longer command at the end is actually changing the replication factor to 4 recursively for everything within this subdirectory. So let's say you previously stored something in that subdirectory with replication factor 3, and you want to add more resiliency to the file system, and you can up that replication factor to 4, or you can bring it down to 2 or 1 after you've actually loaded the files into HDFS. This is a diagram that shows the best practices approach for how to architect a HDFS cluster. So this is how Yahoo sets up their 4,500 node cluster. So we have 3 different racks here. Each rack has 40 slave machines. And every rack has a top of the rack switch. In a Yahoo cluster with 4,500 machines, you have something like 110 racks and 8 core switches. I'm showing 2 core switches here and 3 racks. So every one of the slave machines will have 2 Cat5 cables coming out of it going into the top of the rack switch. So that means the top of the rack switch has at least 80 ports on each rack. And that within the rack, it's a 1 gigabit network. So the connectivity within the rack is 1 gigabit. However, the core switch layer is a 10 gigabit network, of which 8 gigabits are dedicated to HDFS, and the other 2 gigabits are kind of open for MapReduce administration work and just user traffic on the network. This should be a dedicated network, though, at the top of the rack switch layer and at the core switch, dedicated for HDFS and MapReduce. You'll see that some of these racks also have, master nodes like the name node or the job tracker or the HBase master. But if you have 100 racks, a lot of the racks will have no master machines on them. You'll also notice that the master machines are beefier. They're dual or triple redundant hardware machines as opposed to the slave machines, which are usually just one power supply, and there are single points of failures on the slave machines, but that's not as critical because if a slave machine crashes, there are other machines that have a copy of that data. Another feature in HDFS is that the name node is rack aware. So in this slide, we're seeing the same 3 racks as before. Each rack has 5 data nodes. The second rack has data nodes 6, 7, 8, 9, and 10. And you can see that there are 3 replicas of block A. They're on data nodes 1, 7, and 8. And that information is, as you know, kept in the name node's metadata. So the name node knows that this file.txt breaks up into 2 blocks, block A and B. And block A is on 3 different data nodes, and block B is on these 3 different data nodes. Another thing is that the name node is rack aware. That means that the name node knows what rack each data node is on. You have to actually manually configure that on the name node via a bash or Python script. It's pretty simple to do. And now this name node knows that rack 1 has data nodes 1, 2, 3, 4, and 5, and rack 2 has the next 5 data nodes. That rack awareness is going to come into play when you store a file in the cluster, because the name node, when it stores its 3 replicas for each block in the file, the name node wants to scatter those replicas across at least 2 different racks. So if an entire top of the rack switch failure happens, an entire rack goes out of commission, there should still be at least one other rack that has a copy of your data. If there is no rack awareness in Hadoop, then there is a chance that one rack would have gotten all 3 replicas, and if that rack goes down because of a failure, then you will lose those replicas for that point in time that the failure exists. In a smaller Hadoop node, though, with under 20 nodes, you don't need to configure rack awareness. You can configure all 20 nodes to the same switch and just act like they're all on the same rack, which is called the default rack. However, as you start to scale out your cluster, you'll want to use a rack awareness topology script. So with that introduction to HDFS, let's take a little bit deeper dive on how HDFS actually does the writes. On the left here, if you have a client, so that's like your laptop that is outside of the cluster that has a file that you want to load into your Hadoop cluster. So the file you'll want to load here actually breaks up into 3 different blocks, block A, B, and C. And in the cluster, I've kind of removed some of the complexity from the previous slides. So we're only seeing 3 data nodes and 2 racks. However, keep in mind that each rack does have more data nodes, and this is a bigger cluster, but I've removed all of the actors that will not play a role in the write we're going to do for this file. And I've also moved the name node out of the cluster. Keep in mind the name node is rack aware. It knows that data node 1 is on rack 1, and data node 7 and 9 are on rack 5. All right, so when you actually want to store this file with 3 blocks into the cluster, you will basically just run one command called a copy from local command, or you'll write like 5 or 6 lines of Java MapReduce, which will then instruct the client API for Hadoop on your laptop to go through the following steps to actually write the file into the cluster. So you don't have to actually do this yourself, or you don't have to actually break the file up into 3 blocks and then contact the name node to ask, where am I going to store this block. This is done for you by the Hadoop Client API. Like I said, all you have to do is write some simple Java code or run a command line copy from local command. But what happens is the first step is when you submit a file to the client API on your laptop, the client will contact the name node and say, I want to write file.txt block A into the Hadoop cluster. The name node will respond saying, OK, write that block A to data nodes 1, 7, and 9. And then the client will directly contact data node 1 and over TCP 510 send a ready command to data node 1, basically saying, get yourself ready. I'm about to send a block down to you, but also get data node 7 and 9 ready. So then data node 1 will forward on that ready command by hopping through the top of the rack switch, the core switch, and the next top of the rack switch, or to data node 7 and send the ready command and ask 7 to get 9 ready as well. And then finally, data node 9 will let 7 know that it's ready, and 7 will let 1 know that it's ready, and 1 will let the client know that they are all ready and the TCP pipeline is ready to take down that first block. So this is where the pipelined write actually begins. You'll notice that when the client is going to start streaming the block down to the clients, it is not having to go through the name node anymore. The name node is really only used to figure out where in the cluster you will write that block. But then after that, the client contacts one of the data nodes directly to start streaming the block in. So the client will send block A down to data node 1, which will then forward it to data node 7, which will then forward it down to data node 9. And then each one of the data nodes will let the name node know that they received the block successfully. And the first data node will let the client know that they all received that block successfully. And then the client will move on with block B. And block B will be stored in perhaps 3 entirely different data nodes. Right? It's not like the file will be stored on only these 3 data nodes. For the next block, the client will basically renegotiate with the name node the location for block B, which might be an entirely different set of racks and data nodes. I want to point out just a few other things here. You'll notice that we're spanning 2 racks here. This is part of the algorithm for HDFS. Basically, when you write a block into HDFS, it will put the first replica on a rack by itself in a data node. And that first data node is kind of randomly chosen, and that rack is basically kind of randomly chosen. And then the HDFS name node will choose a different rack. In this case, it chose rack 5. And on that rack, it will kind of randomly choose 2 different data nodes to put the second and third replica together on a rack. So the first replica goes by itself on a rack, and replicas 2 and 3 will be more tightly coupled on a rack. The reason for that is because when you write from data node 1 to 7, you have to go through 3 different switches. But to go from 7 to 9, you just have to go through 1 top of the rack switch back down to 9. So that keeps the latency for the write a little bit lower. However, this is a synchronous write. So the client does have to write to 1, 7, and 9 before the write is considered successful. If you reduce your replication factor in HDFS to just 1, then the client only has to write to data node 1, and then a write successful is sent back to the client and the name node. That kind of write is going to be many times faster, 5, 10, 20 times faster than doing a replica 3 write, which is a synchronous write across multiple switches and multiple data nodes. When a client is reading a file, the same type of architecture comes into play. The client has to contact the name node first to figure out where the actual blocks are stored for a file. So in this case, the client is going to ask the name node, what are the block locations for a file called results.txt? And as you can see, the name node has in its metadata the block locations for block A and block B for that file. So the name node will respond back saying, there's two blocks in this file. Block A is on data nodes 1, 4, and 5, and block B is on data nodes 9, 1, and 2. And then once again, like before, the client will directly connect to the data nodes to read the blocks. Now, this list that the name node sends with block A being on 1, 4, and 5 is a ordered list, and this is kind of recommending the client to contact data node 1 first to read the first block. If the client cannot contact data node 1 for whatever reason, then it will move on to data node 4 to read the other replica of the block. The name node is intelligently ordering the list of data nodes based on how much network traffic each data node is under. But the other important thing to once again reiterate here is that the client has to contact the name node just to figure out where to read the files from or where to write the files to. However, the relationship is direct between the client and the actual data nodes for where the write takes place. So it's not like the read or the write is having to flow through the name node to the data nodes. That would make the name node a single point of failure in a large cluster. You can think of the name node kind of like a bookkeeper in a library. So, in a library, if you want to find a book, you're not going to go randomly from shelf to shelf looking for the book. That would take too long. Instead, you prefer to go, to a cupboard and you open up a drawer in which there are a bunch of index cards which have, all the books in the library organized by like author's last name or the title in descending order, for example, right? So you can go open up those index cards and very quickly figure out where your book actually is. And then, so the index card kind of points you towards that shelf, right? That's kind of what the name node is doing here. The name node is kind of like that cupboard with all the index cards which make the file system metadata on the name node. So now I'm going to show you a live demo of how HDFS works. We're running a one-node virtual machine here. I'm currently in Linux in this directory, home Cloudera Maracana demo. And I'm logged in to this Linux machine as a user named Cloudera. And in this directory, Maracana demo, there are two files, shakespeare.txt and tomsawyer.txt. These are just files from Project Gutenberg. So let's take a look at one of these. Let's take a look at shakespeare.txt. It's just a multi-megabyte file that has the entire works of Shakespeare. It's just a text file. And similarly, there's a Tom Sawyer file that has the adventures of Tom Sawyer by Mark Twain. So our goal here is to write these two files into HDFS. Now, since this is a pseudo-distributed one-node cluster, all of the daemons for HDFS and MapReduce are running on this one machine. So the first thing we'll do is just kind of run this Hadoop command, which shows all of the options for Hadoop. We are going to be more focused on this file system option. So let's run that. And we'll see all of the options for the file system. So we can do ls, we can run a du command, a move command, a copy command. So let's actually run the command to list what is in the file system first. So it's Hadoop fs-ls, and we'll list what's at root of HDFS. So we can see that there's 3 folders at root, and these are all 3 each one of them is a directory. Don't be confused between that and the Linux ls command, which is showing me what is in my Maracana demo folder. So let's drill a little bit deeper into the file system. Let's do Hadoop fs-ls, and let's take a look at what's in the user directory. So there's 2 subdirectories here. One of them is named Cloudera, and one of them is named Hive. Remember, I'm logged in as the user Cloudera, so my home folder is user Cloudera. And if I do a ls in there, I don't see any files. So there's nothing in there right now. Let's make a directory first. So we'll do mkdir, And we'll make a new directory in there called new dir. And in here, we'll store the 2 ebook files. So if I run ls now, I should see a directory here called new dir. And if I go into the new directory, I'll see no files. Before I actually load the file into HDFS, let me show you the name node GUI. This GUI is just showing me when the name node was started. It shows me that there's about 137 files and directories in HDFS and 59 blocks total. There's just one data node right now, and there's no dead nodes in the cluster. This cluster is configured capacity is about 4.5 gigs. So when I load the files into the cluster, this number should increment from 137 to 2 more. It should go up to 139 once we load the files in. So let's do that. We do that using the Hadoop copy from local command. So this is a case-sensitive command. We'll do copy from local, and the file was called shakespeare.txt, and I'm going to give it the path in HDFS where I want it to be stored. So user Cloudera new dir, and hit enter. And let me do the same thing with the Tom Sawyer file. And hit enter. And then while I'm here, let me just do a ls command and check what's in user Cloudera new dir. And there you can see the 2 new files I just added in. There's shakespeare.txt and there's tomsawyer.txt. You can see the user, group, and other permissions for that file. This number 1 means that this file is currently replicated once. In a 1-node cluster, this is fine, but in a production cluster, you should usually use replication factor 3. And this is the size of the file in HDFS. Now, if you go back to the name node GUI, and if I refresh this page, if I refresh this page, we should see the file count go up from 137 to maybe 139. There you go, and it's gone up just a bit. One more thing in the name node that's kind of cool is if you go into the browse the file system link, you can also look at what's in the file system through here. So I'm going under user, Cloudera, new dir, and there we go. I should see my 2 files there. And if I click on one of these files, I can see the raw contents of the file as well. I hope you enjoyed this short introduction to HDFS. If you'd like to learn more about HDFS, please check out maracana.com for upcoming dates for a public class for Hadoop. We also do private classes for companies, so if you'd like to contract us out for a 2-day private class, we can do that as well. And this is my email address if you want to send me any questions. I hope you enjoyed the course, and I look forward to seeing you in one of my classes in the future.